I decided to take a little bit of a different approach than you may have expected from Powertrain. Most often I think like people want to talk about, you know, like engines and fire and gas and burning and how you make horsepower and torque and all that jazz, but I didn't think that that was really necessarily relevant, as well as, I mean, to get into the sort of guts of it, it would be a hours and hours long presentation. So I took a bit of a different approach, and hopefully the presentation will sort of give you guys a better understanding of like what my job is when the car is actually running, and how we actually get the engine to run. Yeah. First things first, of course we can't sort of go into the presentation without having a bit of an overview. Formula SA rules state that we have to use an engine that runs on the 4-stroke cycle. I'm going to sort of assume that you guys are all sort of somewhat familiar with it. So, you know, basically, starting at the first picture over there, we've got the intake stroke, which pulls in the fresh charge, you know, so your air and fuel mixture. Then from 1 to 2, you've got your compression stroke, basically where your piston comes up, decreases the volume within your cylinder, and thus increasing pressure and increasing temperature. Then you've got combustion. Basically, you know, we're restricted to running spark ignition engines, again, as per the rules, because they only provide gasoline or ethanol. So, yeah, and then you get your expansion or power stroke. That's where, you know, the torque is delivered to the crankshaft and, you know, the wheels. And then, again, finishing off, 4 to 1, exhaust valves open, all the sort of products of the combustion reaction go out of the exhaust, and you start back at 0. So, PV diagram. So yeah, essentially the way that we control this whole mess of exciting things happening inside the engine is with this. It's essentially, it's called an engine control unit. It's basically the computer that allows you to control how the engine is operating. So basically this is the modern solution to make engines run. In the past it's been quite a few years now. In the past it was all mechanical. So you had mechanical fuel pumps, carburetors, and everything. And basically the way that they worked is just by, you know, drawing vacuum through an orifice, and then it would draw fuel in. There was a meter based on your jets and so on. And it obviously worked for a long time, but it's limiting in the sort of application today now that you can precisely control an engine with a computer, essentially. And yeah, so there's, in order to use an engine control unit like this, there's essentially 3 sensors that are necessary. So, first of all, we've got the crank position sensor. So this is actually a picture of ARC crank position sensor from our engine. So you see here, this is actually a flywheel, and it's got a trigger wheel that goes around it. And then the sensor itself is this guy right here. And then this is the magneto and so on. So what it does is that you've got all these teeth along the circumference of the flywheel here. And then you've got that gap of the missing tooth. Right? So this setup is called the 36-2. There's 36 teeth, 2 missing teeth. So this is essentially the waveform that we get. The sensor type is called a variable reluctance sensor. It sort of operates on the same, I think most of you are familiar with sort of speed sensors and so on. Often people refer to them as just Hall effect sensor, sort of a blanket term. But a Hall effect sensor is one type of sensor, whereas variable reluctance sensor is another type of speed sensor. A Hall effect basically gives a square waveform, so it's either on or off. So as a tooth passes by the magnetic sensor, it'll say yes or no, essentially. Whereas a variable reluctance sensor actually sort of acts more as a proximity sensor. So in between each teeth, you've got these waveforms, like a sine wave, that fall off as the magnetic field becomes or decreases in strength, and then increases again as the next tooth gets closer. So this is very useful for us in terms of crank position sensor, because it actually allows us to interpolate in between peaks to get finer angle measurements, essentially. Because, for example, on our engine we've got 36.2, which if you assume that from like a Hall effect sensor standpoint, that would only give you around 10 degrees of resolution around your whereas a variable reluctance sensor, since the magnetic field is changing as the teeth are getting either closer or farther away, you can interpolate based on the speed of the engine, and this is all within the computer, to precisely sort of understand where your engine actually is. So it gives approximately a resolution of 1 degree or so. Yeah, so then this point right here is where you see the missing teeth, and this is where basically you tell the ECU based on sort of where that missing tooth is in reference to where the piston is. So this is sort of in a geometrical sense. So you tell the ECU when that happens based on top dead center, so when the piston is closest to highest in its stroke. And then after that point, it'll start counting, and it'll count peaks until the point where, say, you set your spark timing or your fuel timing. And then I'll get into that. Next thing, or next necessary sensor, is the engine load sensor. So essentially there's two different sensors. There's the manifold air pressure sensor, or a throttle position sensor. So this is essentially the manifold air pressure sensor. Basically, as the vacuum within your intake decreases, your voltage increases, and yeah. So, for example, here you can see that on idle you're running sort of near atmospheric pressure in your intake, and then on accelerating either here or here, you go up to high vacuum as the engine is pulling in substantially more air through the intake. The next way is throttle position sensor. So this is sort of a crude sort of way in a certain sense, although it works very well. And this is actually what we use. Basically what you're doing here is you're just measuring the angle at which the throttle plate, you can imagine most throttles are usually just a plate type that rotates. So you're just measuring the position of that throttle plate, and then based on the calibration of your engine, you can sort of determine the operating condition that the engine is in. And yeah, again, voltage increases as the throttle opens. So yeah, those two types of sensors allow for two different types of fuel metering. You've got your alpha N, which runs on the TPS, and you've got speed density, which is using a map sensor. Alpha N basically stands for, or the alpha part of the alpha N is the angle of the throttle plate, and N being the RPM, or the revolution per minute of the engine. And then speed density is basically, it's sort of an estimation using the ideal gas law of the airflow based on pressure and temperature. So yeah, we use alpha N, so I'll sort of focus on that for the most part. This is sort of a snapshot of, well, it's actually our ECU interface, but it's not from our engine. Just pulled it off the internet. But essentially here you can see on the left side there, the vertical axis, that we've got manifold air pressure. In our case that would be throttle position, and then along the x-axis you've got RPM. So basically this defines, this map, which is called your fuel map, defines the operating condition which your engine is in. And then these numbers stand for the pulse width that your injector is open for. So basically this is milliseconds. So here you'd be seeing as RPM increases essentially, you'd be keeping your injector open for longer. As, in most cases the engine makes more power at higher RPM, thus it needs more fuel, it's getting more air, and so on. Again, another representation of the same thing. Instead of having numbers in the sort of z-axis, we've actually got contours. So again, RPM, TPS, and then you can sort of see high spots here where you can tell like this is where you're making power and torque or whatever you want to visualize that. And then, so that's the fuel meter inside of it. Of course, back to the crank position sensor. There's, it's all fine to have the perfect fuel, stoichiometric or whatever you want to be running coming into your engine, but you need to know when to ignite that mixture. So essentially, the big thing here is that as RPM increases, you need to advance your ignition timing, and that's essentially because, given the speed of your engine, you need more time to basically, because there's a fixed burn time in which your fuel air mixture will burn. There are other variables, for example your air fuel ratio and so on. But if we assume that it's constant, as your engine speed increases, that time stays the same. So you need more crank angle degrees to allow that fuel air mixture to burn properly. Because essentially what you want to do is you want to have the sort of peak cylinder pressure occur just slightly after the top dead center point, such that you get the maximum torque pushing down, or pressure in the chamber pushing down on the piston, and thus producing maximum torque. And then here you see it's just an example of a sort of a timing table. Again, the sort of axes are a bit mixed up. Throttle position on the top there. RPM is increasing vertically there. So you see at low RPM, even high load, there's hardly any advance here. High load conditions often mean that your engine's running quite hot, which sort of slow it. If you have more temperature, your burn rate increases, thus you need less timing to achieve the same point of maximum cylinder pressure after top dead center. And then as RPM increases, you see it increases all the way up to a maximum of 60 degrees there. And that's sort of important because, in the ideal world, you'd want to advance your timing to the least amount as possible, because that reduces the amount of negative work you're doing on that your engine is doing. Because if you start your ignition too early, then even if your burn rate of your air fuel mixture is quite fast, your engine will still be going upwards in its stroke, and thus you're counteracting the work that is being done by or the possible energy released by the air fuel mixture burning, by that happening too early, and thus putting a negative force on the piston, trying to slow it down before it gets around back to top dead center. And yeah. Questions? Yeah.
So you were saying how as the engine goes faster, you're gonna ignite sooner, right?
Yes.
So is that something that you play with, and you test, or is that already programmed?
No, so all of these parameters are something that we adjust ourselves. So given, even a small change like the diameter of your exhaust runner, for example, that'll change how your engine is breathing, and thus change the amount of air that you can actually pull into your engine, and thus change the amount of fuel that you need to supplied to your engine, and thus changing the timing that you need to. So timing is a bit of it's sort of a bit more complicated than just sort of picking a best number. Often you can try to tune for best torque and get that point at which your engine produces the maximum amount of torque with the least amount of vent. But you often, in the case of spark ignition engines, you run into issues with knock or pre-detonation of your air-fuel mixture, i.e. your mixture igniting somewhere else other than at the point where you actually spark your spark plug. Answer your question.
So the ECU is all those sensors, but what variable does it actually control? Is it just the ignition timing?
No, so it's basically with those maps, you basically calibrate those maps. That's what one does on the dyno and fine tuning in the car. And you have those base maps set up already, and so it's controlling the ignition timing and the fuel delivered to the engine. But that's based on whatever driver sensor is equipped. So in this case, the sort of independent variable is throttle position, which then, based on the throttle position signal, the ECU will figure out where it is in the RPM range and how much fuel it needs based on the load. And so on. But yeah, they're all calibrated beforehand. The ECU it doesn't know anything about the engine, right? It can't guess at how much fuel it needs, and it can't guess at how much spark timing it needs. So that's why one spends a lot of time on the dyno trying to sort of yeah.
How do you model on the dyno, intake air in the sense that when you're driving it's coming in at a certain velocity, but when you're on the dyno it's stationary?
Yeah, so that's something that's always difficult to calibrate, and often what people do is just they'll tune it based on just no airflow, so entirely dependent on the value produced by the engine, and then once you actually install your system in the car, inside the car, then they'll sort of do fine-tuning adjustment based on temperature, pressure, atmospheric conditions, as well as then, if you have what's called ram air, where the air is actually forced into the intake, then of course you have to have a compensation for that. Cool. Get that engine RPM, right? So that's how the TPS or throttle position or the map sensor acts as the load on the engine, because based on the amount that you're, for example, the amount that you're pushing the throttle, it'll be able to figure out the load. Once again, I don't know if I explained that very well.
So is it per gear then?
No. So, how do I explain it better? If you had no load on the engine, i.e. nothing braking your engine from accelerating, then yes, you probably wouldn't be able to get past 10-15% throttle before you'd be redlining your engine, hitting your air limiter, because there's nothing stopping it from accelerating, right? But when you do have a load on the engine, thus your engine is actually supplying power to accelerate the vehicle, for example, based on your velocity, you'll require a certain power to continue to accelerate, right? So again, based on the speed that you're at and the gear that you're in, that'll define the load in a certain sense. But that's directly related to the throttle position that you're at.
It's like, I think maybe another way to say is that like TPS and RPM kind of, they define the operating like parameters of your engine at that moment in time, and what you're adjusting is you're trying to see like what the like best like fueling parameter is for that option. So it doesn't matter if TPS and RPM are somehow linked. The point is that you need those two variables to, because if you define a TPS, you can't automatically know what your RPM is, and vice versa, because like Lou said, it depends on your gear, it depends like, you know, how fast was the car going before you started accelerating, and all that. So it's like, yeah, they're kind of linked, but you still need to know both of them in order to make kind of the decision of what your fueling should be like. I don't know if that...
So like dynoing is just a matter of adjusting different loads and pinpointing those cells, you know, the parameter of RPM and TPS, and then you modify respectively like which values will create like what Lewis mentioned before, stoichiometric, which is like complete air fuel mixture.
Yeah, well, so essentially, like, if we want to get into a little bit of like how one actually tunes the fuel map and the emission map on the dyno, one common way is that, like, for example, if you're taking power curves, like we used to do at Seb shop, chassis dyno, for example, is that you basically define a sweep rate, i.e. like a RPM increase rate, and that's controlled by the dyno computer. And then you set your initial RPM, and then you go full throttle, and then the computer running the dyno will adjust the load based on your sweep rate, and essentially allow you to accelerate along one line. So for example, if this is 100% throttle, you know, you're starting at say idle, 2,000 RPM, you go full throttle, and then it'll adjust the load, so you go directly across the top, and adjust your fuel and your emission that way. And like that's how you pull power curves that you see, power or torque, is it's all 100% throttle. Yeah, so I mean the way you accelerate your engine is by removing load. So you start off and you're at max load for that condition, and then you slowly pull load off so that the engine will accelerate.
Like, how do we do it in the shop?
Yeah, I mean it's the same thing. So for us, instead of having basically large drums that are being rigged, we have a small little water turbine, and you essentially control the flow rate of the water through the turbine, and that supplies your load that you then use to control your engine to define its operating conditions. So I mean, in the ideal world, you would set up like your dyno calibration would involve tuning every single load site that you might possibly see. But at the same time, a lot of these load sites, like for us, there's whole sections of the fuel map that we've never even seen, because you can't realistically get there. Like you can't be at 10,000 RPM into a percent throttle. Any more questions?
Yeah, what was VE on the
Yeah, so that's volumetric efficiency. So basically it's a measure of the air that is being drawn into the engine over the engine's displacement. And displacement being the bore times the stroke. So yeah, it's a measure of how like efficiently your engine is drawing in air. And since you have a known maximum displacement, then you can sort of based on volumetric efficiency, you can guess at how much air is actually coming into your engine.